March 19th, 1944. A Republic P-47 Thunderbolt screamed across the German sky at 420 miles per hour, its massive Pratt and Whitney R-2800 engine roaring with a power that shouldn't have been possible. Inside the cockpit, Captain Robert Johnson watched his manifold pressure gauge climb past 65 inches of mercury, then 70, then 72. The needle shouldn't have been there. The engine shouldn't have survived. But it did, because the fuel flowing through those cylinders wasn't supposed to exist. 3,000 miles away, in a laboratory at Wright Field, Ohio, a Shell oil chemist named Geoffrey Russell had broken every rule in the book to create it. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The story of how American fighters came to dominate European skies doesn't begin with brave pilots or superior aircraft design. It begins with a number, 100, the octane rating that defined aviation fuel in 1939. The British were burning 87 octane. The Germans had pushed to 96. The Americans were experimenting with 100. But Geoffrey Russell believed they could go higher, much higher, and in doing so, would hand Allied pilots a weapon the Axis powers couldn't match. The problem was that every conventional approach to increasing octane had been exhausted. The chemistry seemed to have reached its limit. What Russell proposed wasn't just unconventional, it bordered on industrial heresy. The chemistry of octane is deceptively simple in theory, brutally complex in practice. Octane rating measures a fuel's resistance to premature detonation, what pilots call knock. When an aircraft engine compresses its fuel-air mixture, the mixture heats up. If the fuel ignites before the spark plug fires, the resulting shockwave can destroy pistons, crack cylinder heads, and turn a 27-litre radial engine into scrap metal in seconds. Higher octane fuel can withstand higher compression ratios and higher boost pressures without detonating. Higher compression means more power from the same displacement. More boost means more air forced into the cylinders. Together, they transform an engine's capability entirely. In 1939, the world's aviation powers were locked in a desperate race to increase octane ratings. Britain's Royal Air Force had learned painful lessons during the Battle of France. Their Hurricane and Spitfire fighters, running on 87-octane fuel, couldn't maintain combat power for extended periods. German Messerschmitt Bf 109s, using 96-octane with water methanol injection, could push their Daimler-Benz engines beyond rated limits during critical moments. The difference of 9 octane points translated to altitude advantage, speed advantage, climb advantage. It translated to pilots living or dying. The United States Army Air Corps had been experimenting with 100-octane fuel since 1936, but production was limited and the formula was expensive. Standard 100-octane required precise blending of high-grade alkylates, catalytic reformates, and aromatics, all expensive to produce. The petroleum industry had optimized this process as far as conventional refining technology allowed. To go beyond 100-octane, someone would need to break the rules. Geoffrey Russell was prepared to do exactly that. Russell had joined Shell Oil Company's research division in 1937 after completing his doctorate in organic chemistry at the University of California. His specialty was catalytic cracking, the process of breaking heavy petroleum molecules into lighter, more valuable products. By 1940, he was working on aviation fuel development at Shell's Emeryville, California research facility. The British had approached American petroleum companies with an urgent request. They needed more 100-octane fuel, immediately, for their fighter command. The Battle of Britain was approaching, and every octane point mattered. Russell studied the existing 100-octane formulas and saw their limitations. Conventional high-octane fuels relied on specific hydrocarbon compounds, isooctane, and aromatic compounds like toluene and xylene. These compounds had excellent anti-knock properties but were expensive to produce and required specialized refinery equipment. Production couldn't scale fast enough to meet wartime demand. Russell proposed an alternative approach. Instead of refining base fuel to higher standards, he would add compounds that would suppress knock-through chemical action. The idea wasn't new. Lead tetraethyl had been used as an anti-knock additive since the 1920s, but Russell believed different compounds could be more effective. His breakthrough came from an unexpected source, studying fuel samples that the British had captured from downed German aircraft. The Luftwaffe wasn't using pure high-octane fuel, they were using lower-grade base fuel enhanced with aggressive chemical additives. Russell identified methylcyclopentadienyl manganese tricarbonyl, a compound so obscure that most chemists had never heard of it. The Germans were using minute quantities as a combustion modifier. Russell realized that with proper formulation, similar compounds could boost effective octane ratings far beyond what conventional refining could achieve. The chemistry was elegant. These organometallic compounds acted as radical scavengers during combustion, intercepting the chain reactions that caused knock before they could propagate. A small amount of the right compound could make 95-octane base fuel perform like 115-octane refined fuel. The cost savings were enormous. The production implications were revolutionary. There was just one problem. The compounds Russell wanted to use weren't approved by the Army Air Corps technical specifications. They weren't banned. They simply didn't exist in the official fuel standards. Using them would require rewriting the rules. Russell prepared his proposal in December 1940. The mathematics were compelling. By using specialized additives, Shell could produce fuel with an effective octane rating of 115 to 120 at roughly 70%, the cost of conventional 100 octane. Production capacity could increase by 40% using existing refineries. But the fuel would require engine testing, lots of it, because nobody knew how these additives would perform under combat conditions. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The proposal reached Wright Field, Ohio, in January 1941. The Army Air Corps, Materiel Command's Fuels and Lubricants Laboratory, was responsible for testing and approving all aviation fuels. Major Donald Putt, chief of the Aircraft Engine Research Section, read Russell's proposal with growing interest. The Army had just ordered the Republic P-47 Thunderbolt into production. The Thunderbolt was designed around the massive Pratt and Whitney R-2800 double wasp engine, a radial powerhouse displacing 2,800 cubic inches. With standard 100-octane fuel, the engine produced 2,000 horsepower for takeoff and could sustain 1,800 horsepower at altitude with its turbocharger. Putt understood immediately what Russell's fuel could mean. The R-2800's limiting factor wasn't mechanical strength, it was fuel octane. The engine could handle far higher cylinder pressures than 100-octane fuel would allow. With 115-octane fuel, boost pressure could increase from 52 inches of mercury to 65 or even 70 inches. Power output would jump proportionally. A 2,000 horsepower engine could become a 2,300 horsepower engine, possibly 2,500. The performance implications were staggering, but Putt also understood the risks. Aviation fuel specifications existed for good reason. Fuels had to perform consistently across extreme conditions, from -40 degrees Fahrenheit at altitude to 120 degrees on tropical runways. They couldn't corrode fuel systems, couldn't form deposits in carburetors, couldn't break down during storage. Russell's additives were unproven in operational conditions. If the fuel failed in combat, pilots would die. If it damaged engines, the entire fighter force could be grounded. Putt authorized preliminary testing in February 1941. Shell delivered 55-gallon drums of experimental fuel to Wright Field. The first test engine was a Pratt and Whitney R-18, 100 Wasp, a smaller radial engine used in training aircraft. Engineers installed it on a test stand, connected instrumentation, and began cautiously increasing boost pressure. At 55 inches of mercury, the engine ran smoothly, producing its rated horsepower without knock. At 60 inches, still smooth. 65 inches, no problems. At 70 inches of mercury, the experimental fuel was suppressing knock that would have destroyed the engine with conventional 100 octane. The initial results were promising, but engine test stands don't replicate combat conditions. An aircraft engine experiences constantly varying loads, temperatures, and pressures during flight. It operates at extreme altitudes where atmospheric pressure drops to a fraction of sea level. It must restart reliably after being shut down at high altitude. It must tolerate violent maneuvers that slosh fuel in the tanks and create vapor locks in fuel lines. The only way to truly test Russell's fuel was to put it in operational aircraft and fly them hard. In March 1941, the Army selected 6 Curtiss P-40 Warhawk fighters for fuel testing. The P-40 used the Allison V1710 inline engine, a 12-cylinder liquid-cooled design producing 1,040 horsepower on 100 octane fuel. The test pilots were instructed to push the aircraft beyond normal limits, climbing to maximum altitude, diving at maximum speed, performing violent aerobatic maneuvers. They were testing whether Russell's fuel would cause vapor lock, whether it would foul spark plugs, whether its combustion characteristics would remain stable. The pilots reported no problems. The fuel burned cleanly, left minimal deposits, and didn't vapor lock even during extreme altitude changes. More significantly, when pilots were authorized to increase boost pressure above normal limits, the engines responded with dramatic power increases. At 65 inches of mercury manifold pressure, roughly 20% above normal maximum, the Allison engines produced 1,250 horsepower, a 20% increase. The P-40s climbed faster, flew faster, and had better high-altitude performance than any P-40 that had flown before. But the Army remained cautious. The P-40 was already in production and operational. Changing its fuel specification would require modifying thousands of aircraft in the field, retraining mechanics, restructuring supply chains. The risk seemed too high for an aircraft already committed to combat. The place to introduce Russell's fuel was in a new aircraft, one designed from the beginning to exploit its capabilities. The Republic P-47 Thunderbolt was that aircraft. The P-47's development had been troubled. Republic Aviation had designed it around the R-2800 engine and a revolutionary turbocharging system. The turbo supercharger, mounted in the rear fuselage, would compress thin, high-altitude air and force, put it into the engine, allowing the Thunderbolt to maintain sea-level power at 30,000 feet. In theory, the concept was brilliant. In practice, the aircraft was overweight, underpowered, and suffering from endless technical problems. The prototype had first flown in May 1941 and immediately revealed issues. At 27,000 pounds gross weight, the P-47 was the heaviest single-engine fighter ever built. Its rate of climb was mediocre. Its acceleration was poor. Test pilots reported that German Messerschmitt Bf 109 fighters and Focke-Wulf WWII fighters could outclimb it below 15,000 feet. The Thunderbolt's advantage was at high altitude, where its turbocharger gave it power that German fighters couldn't match. But getting to high altitude took time, and in combat, time meant the difference between attacking and being attacked. Republic's engineers knew the solution was more power. The R-2800 engine had been conservatively rated to ensure reliability, but it was capable of much more. The limiting factor was fuel octane. With 100 octane fuel, boost pressure was restricted to 52 inches of mercury to prevent destructive knock. With Russell's 115 octane fuel, those limits could be dramatically raised. In June 1941, the Army authorized Republic to conduct high-octane fuel tests on the P-47 prototype. The results exceeded everyone's expectations. With boost pressure increased to 65 inches of mercury, the R-2800 engine produced 2,200 horsepower for takeoff and maintained 2,000 horsepower to 25,000 feet. The Thunderbolt's rate of climb improved by 30%. Its top speed increased from 412 miles per hour to 433 miles per hour. Most dramatically, its acceleration improved enough that pilots could actually use the aircraft's weight advantage, diving away from threats and using speed to disengage from unfavorable combat situations. Major Putt recognized that Russell's fuel had transformed the P-47 from a marginal design into a potential war winner. But there was still the problem of official approval. The fuel didn't meet Army Air Corps specifications because those specifications didn't include provisions for the additives Russell was using. Changing the specifications would require extensive documentation, metallurgical studies, long-term storage tests, and approval from multiple bureaucratic levels. The process normally took years. The United States didn't have years. In December 1941, Japan attacked Pearl Harbor. America was at war. The bureaucratic situation became urgent in early 1942. The Luftwaffe was flying new fighters, the Focke-Wulf FW-190A3, powered by the BMW 801 radial engine. German pilots reported the new fighter had excellent performance and could outmaneuver American P-38 Lightnings and P-40 Warhawks at most altitudes. Intelligence reports suggested the Germans were using improved fuel, possibly 100 octane or higher with aggressive additives. If German fighters had fuel advantages, American pilots would pay with their lives. General Henry Arnold, commanding general of the Army Air Forces, cut through the bureaucracy in March 1942. He issued a directive: all new fighter aircraft would be cleared for operation on 115-octane fuel. Official specifications would be updated retroactively, testing would continue but would not delay deployment. It was a calculated risk, but Arnold believed the performance advantages outweighed the potential problems. Geoffrey Russell's experimental fuel became official, though the official designation was carefully neutral: ANF-28, grade 115, 145 fuel. The designation reflected the fuel's dual rating. It had a lean mixture octane rating of 115 and a rich mixture rating of 145. The rich mixture rating mattered for combat power, those brief moments when pilots pushed engines beyond normal limits to climb, accelerate, or escape. With 145 octane rich mixture rating, the R-2800 engine could briefly tolerate manifold pressures approaching 75 inches of mercury, producing power outputs approaching 2,800 horsepower. For short periods, under the right conditions, the Thunderbolt would become the most powerful single-engine fighter in the world. Production of the new fuel began in April 1942 at Shell refineries in California, Texas, and Louisiana. Other petroleum companies quickly licensed Russell's formulation and began their own production. By August 1942, monthly production exceeded 10 million gallons. By December, it reached 30 million gallons. The fuel was expensive, roughly twice the cost of standard 100 octane, but the performance advantages justified the expense. Every gallon represented potential altitude advantage, speed advantage, survival advantage for American pilots. The first operational P-47 Thunderbolts, equipped to use 115-octane fuel, arrived in England in December 1942 with the 56th Fighter Group. The group's commanding officer, Colonel Hubert Zemke, was a combat veteran who understood aircraft performance intimately. When Zemke learned his Thunderbolts could use high-octane fuel to temporarily boost power output by 40%, he immediately grasped the tactical implications. The Thunderbolt could use its weight and power to dive on German fighters, attack, and use speed to escape before the enemy could respond. It was a completely different combat doctrine than the turning dogfights that characterized fighter combat. But before the doctrine could be tested, the pilots had to learn how to use their aircraft's capabilities without destroying their engines. The R-2800 engine was reliable when operated within limits, but pushing beyond those limits required skill and judgment. Too much boost pressure for too long would melt pistons, seize bearings, or cause catastrophic mechanical failure. Pilots had to understand exactly how far they could push and for how long. The training took months, but by spring 1943, Zemke's pilots were ready to take their supercharged Thunderbolts into combat over Europe. April 17, 1943, 26,000 feet above the Dutch coast, 8 P-47 Thunderbolts of the 56th Fighter Group encountered 12 Focke-Wulf W-190 fighters, climbing to intercept a formation of B-17 bombers. The German fighters had altitude advantage, diving from 30,000 feet with the sun behind them. tactics, the Thunderbolts would have been at a severe disadvantage, forced to turn and fight aircraft specifically designed for maneuverability. But Colonel Zemke had trained his pilots differently. Instead of turning to meet the attack, they pushed their throttles forward and dove. The Thunderbolt pilots watched their manifold pressure gauges climb past 60 inches of mercury, then 65, then 70. The R-2800 engines roared with power that conventional 100-octane fuel could never have sustained. At 72 inches of mercury, each engine was producing roughly 2,600 horsepower, transforming the heavy fighters into screaming projectiles. The Thunderbolts accelerated past 450 miles per hour, then 470, then 500. The German pilots, accustomed to lighter fighters that could turn inside anything, suddenly found themselves chasing targets they couldn't catch. Lieutenant Robert Johnson, flying as Zemke's wingman, later described the sensation. The whole aircraft shook with power. The engine note changed pitch, became deeper, more aggressive. You could feel the thrust pushing you back in the seat. The airspeed indicator climbed so fast you thought it was broken. And the Germans, they just fell behind. They couldn't believe a fighter that size could move that fast. We'd make one pass, hit them hard, then use our speed to climb back to altitude before they could react. It was like fighting with a completely different aircraft. The engagement lasted 11 minutes. The Thunderbolts destroyed 3 Focke-Wulf fighters without loss, but more significantly, they prevented the German fighters from reaching the bomber formation. The tactical success proved Zemke's doctrine. The Thunderbolt wasn't a dogfighter, it was an energy fighter, using superior power and speed to dictate combat terms. And that superior power came directly from Geoffrey Russell's fuel formula. Without 115-octane fuel, the tactics wouldn't have worked. The Thunderbolts would have been forced into turning fights where German fighters held the advantage. The success of April 17th caught the attention of 8th Air Force headquarters. General Ira Eaker, commanding the 8th Air Force, had been skeptical of the P-47 when it first arrived. He considered it too heavy, too cumbersome for European combat. But the engagement over Holland changed his assessment. If the Thunderbolt could use its power advantage to dominate high-altitude combat, it could protect the bomber formations that were suffering devastating losses to German fighters. Eaker authorized expanded use of high-octane fuel and ordered all P-47 groups to adopt Zemke's tactics. But using 115-octane fuel to its full potential required more than just aggressive throttle use. Pilots needed to understand the relationship between manifold pressure, RPM, cylinder head temperature, and time. Push too hard for too long, and the engine would destroy itself. Push at the wrong moment, and you'd waste fuel without gaining tactical advantage. The Army Air Forces established specialized training programs to teach pilots how to manage their engine's capabilities. Captain Hub Zemke, promoted and given command of the 56th Fighter Group, developed a training regimen that treated engine management as a combat skill equal to gunnery or formation flying. His pilots learned to monitor their engine instruments constantly, reading cylinder head temperatures and oil pressures the way a surgeon reads vital signs. They learned that 70 inches of mercury could be sustained for roughly 5 minutes before cylinder head temperatures entered dangerous territory. They learned that 75 inches could be used for perhaps 90 seconds during critical moments. They learned to plan their attacks around these limitations, using maximum power only when it would deliver decisive advantage. The training paid off in summer 1943. As the 8th Air Force intensified its daylight bombing campaign over Germany, P-47 groups began escorting bombers deeper into hostile territory. The extended missions required careful fuel management, balancing the need for combat power against the requirement to return home. Pilots learned to cruise at economical settings, conserving fuel and engine life, then unleash full power when engaging enemy fighters. The technique was called boom and zoom, climbing high on economical power, diving to attack with maximum power, then climbing back to altitude before enemy fighters could respond. The Luftwaffe struggled to counter these tactics. German fighter pilots had trained extensively in dogfighting techniques, emphasizing tight turns and slow-speed maneuvers. Their aircraft, particularly the Bf-109 and FW-190, excelled at these maneuvers. But against Thunderbolts that refused to fight, and on German terms, their training became irrelevant. Major Heinz Baer, a Luftwaffe ace with over 100 victories, noted in his combat report after an engagement in July 1943 that the American heavy fighters were using new tactics that exploited superior speed and power, making interception increasingly difficult. The Germans attempted various countermeasures. They tried diving away from Thunderbolt attacks, but the American fighters could dive faster. They tried climbing above the American formations, but the turbocharged Thunderbolts could maintain power at altitudes where German fighters struggled. They tried coordinated attacks from multiple directions, but the Thunderbolts' speed allowed them to disengage from unfavorable situations. The fundamental problem was that German fighters lacked the power-to-weight ratio to match American fighters using high-octane fuel. By August 1943, German fighter losses over Western Europe were climbing steadily. The Luftwaffe was losing experienced pilots faster than training schools could replace them. Part of the loss rate came from superior American numbers and tactics, but a significant factor was the performance advantage that 115-octane fuel provided. American fighters could choose when to fight and when to disengage. They could protect bomber formations more effectively. They could survive encounters that would have been fatal with lower-performance aircraft. The success of Russell's fuel in combat prompted the Army Air Forces to push for even higher performance. If 115-octane fuel could boost power by 20%, could higher octane ratings provide even more? In September 1943, Wright Field engineers began testing experimental fuels with octane ratings approaching 130. The chemistry became increasingly exotic, using rare additives and complex refining processes. But the performance gains were marginal compared to the production costs. The sweet spot appeared to be around 115 to 120 octane, where cost, production capacity, and performance intersected optimally. Meanwhile, Republic Aviation was developing improved versions of the Thunderbolt that could better exploit high-octane fuel. The P-47D model, entering production in early 1943, incorporated lessons from combat operations. It had increased fuel capacity for longer range, improved cockpit visibility, and strengthened airframe components to handle the increased loads from high-power operations. Most significantly, it was cleared for operation at higher manifold pressures than earlier models. With 115-octane fuel, the P-47D could sustain 70 inches of mercury manifold pressure, producing 2,400 horsepower continuously rather than just briefly. The improved performance transformed escort operations. P-47 groups could now accompany bomber and formations all the way to targets in Western Germany, engaging German fighters throughout the mission. The extended range and sustained high power made the Thunderbolt the dominant fighter in European skies through late 1943. But the aircraft's greatest test was yet to come. In autumn 1943, the 8th Air Force began planning missions deep into Germany, targeting aircraft factories, ball-bearing plants, and oil refineries. These missions would require fighters to penetrate hundreds of miles into hostile territory, fighting their way in and out against concentrated German defenses. The missions would test every aspect of the P-47's capabilities, including its ability to sustain high-power output over extended periods. October 14, 1943, Black Thursday. 291 B-17 bombers attacked the ball-bearing factories at Schweinfurt, Germany. The raid was a disaster. German fighters attacked in waves, destroying 60 B-17s and damaging 138 others. More than 600 American airmen were killed or captured. The Thunderbolts had escorted the bombers as far as their fuel allowed, then were forced to turn back, leaving the bombers unprotected for the crucial final leg to target and back. The Schweinfurt disaster proved that even with 115-octane fuel, the P-47's range was insufficient for deep penetration missions. The aircraft needed drop tanks for extended range, but external fuel tanks created drag that reduced performance. Republic engineers worked frantically to develop streamlined drop tanks that would minimize performance penalties. By December 1943, they had perfected teardrop-shaped tanks that added range without destroying the aircraft's speed advantage. But drop tanks alone weren't enough. The Thunderbolt needed to maintain high performance, even when carrying extra weight. This required careful engine management and optimal use of high-octane fuel. Pilots learned to cruise on economical settings until they encountered enemy fighters, then drop their external tanks and switch to maximum power. The technique required precise timing and situational awareness, but it allowed Thunderbolts to escort bombers to targets throughout Germany. January 1944 brought a new challenge. The Luftwaffe had begun using improved tactics, forming large fighter formations that would mass against bomber streams, overwhelming escort fighters through sheer numbers. The Germans called it Großer Schlag, the big blow. Against these concentrated attacks, individual pilot skill mattered less than raw performance. The side with more power, more speed, and better altitude capability held the advantage. The P-47 groups responded by pushing their engines harder. Pilots routinely operated at 70 to 72 inches of mercury during combat, accepting increased engine wear in exchange for tactical advantage. Maintenance crews worked around the clock, replacing worn cylinders, changing spark plugs, and monitoring engine condition. The high-power operations were taking a toll on engine life, but they were keeping pilots alive and bombers protected. Geoffrey Russell, monitoring reports from Europe, recognized that his fuel formula was being used in ways he hadn't anticipated. He had designed it to provide occasional power boosts during critical moments, but combat pilots were using maximum power routinely. The engines were holding up, testament to Pratt and Whitney's robust design, but Russell worried about long-term reliability. He began work on improved formulations that could provide the same anti-knock protection with less aggressive additives, hoping to extend engine life without sacrificing performance. By February 1944, the strategic air campaign over Europe had reached a critical phase. The Luftwaffe was bleeding experienced pilots, but it remained a potent force. American bomber losses continued at unsustainable rates. The 8th Air Force desperately needed a decisive advantage, something that would shift the air superiority balance permanently. That advantage would come from an unexpected source, not new aircraft or tactics, but a refinement of Russell's fuel formula that would push the R-2800 engine to power outputs nobody thought possible. Shell Oil's research team, working with Wright Field engineers, had identified ways to boost the fuel's rich mixture rating from 145 to 150. The improvement seemed modest, just 5 octane points, but it translated to manifold pressures approaching 78 inches of mercury. At those pressures, the R-2800 engine would produce power outputs approaching 2,800 horsepower. The Thunderbolt would become faster, would climb better, and would have performance margins that could overcome any tactical disadvantage. The improved fuel, designated ANF-28A, began reaching Europe in March 1944. Fighter groups received strict instructions on its use. The fuel could provide extraordinary power, but only for brief periods. Sustained high-power operation would destroy engines within hours rather than days. Pilots had to use the fuel intelligently, reserving maximum power for critical moments when survival or mission success hung in the balance. The first combat test of the improved fuel came on March 19th, 1944. Captain Robert Johnson, now leading a flight of 4 Thunderbolts, encountered a formation of Messerschmitt Bf 109 fighters at 28,000 feet. The German fighters had altitude advantage and were diving to attack. Johnson pushed his throttle to the stop and watched his manifold pressure gauge climb to 78 inches. The engine response was immediate and dramatic. His Thunderbolt accelerated like it had been launched from a catapult, climbing through the German formation with such speed that enemy pilots couldn't track him. Johnson later described the experience as flying a different aircraft entirely. The power was almost frightening. You could feel it in every control input, every maneuver. The climb rate was incredible, probably 4,000 feet per minute or better. I remember thinking that this was what the Thunderbolt should have been from the beginning. This was the aircraft's true potential finally being realized. And it was all because of fuel, something most pilots never even thought about. The engagement demonstrated that Russell's refined formula had achieved what many thought impossible. It had taken an already formidable fighter and transformed it into something that could dominate any opponent. The Thunderbolt pilots now had an aircraft that could fight on their terms at any altitude, against any enemy, with confidence that their power advantage would see them through. The heavy fighter that critics had dismissed as too large and too slow had become the most feared American fighter in European skies, not through revolutionary design, but through revolutionary chemistry. The spring of 1944 brought Big Week, a concentrated campaign to destroy the Luftwaffe's fighter production capacity. From February 20th to 25th, the 8th Air Force launched massive bombing raids against German aircraft factories, while P-47 groups fought to control the skies above. The week would become the proving ground for everything Geoffrey Russell's fuel had made possible. The Thunderbolt pilots would face the largest concentrated fighter resistance of the entire war, and their survival would depend entirely on the power flowing through their engines. February 20th, 1944. The first mission of Big Week targeted the Messerschmitt factory at Leipzig, over 500 miles deep into Germany. Colonel Zemke led the 56th Fighter Group into German airspace, knowing his pilots would face hundreds of enemy fighters. The Luftwaffe had concentrated its resources, pulling fighter units from across Europe to defend the aircraft plants. German commanders understood that if these factories fell, Germany's ability to replace fighter losses would collapse. They were prepared to sacrifice everything to stop the American bombers. The first German fighters appeared at 28,000 feet, climbing through broken clouds. Zemke counted at least 60 Bf-109 fighters in a single formation, with more joining from the east. Standard tactics called for Thunderbolts to maintain formation and protect the bombers, but Zemke recognized that passive defense would fail against such overwhelming numbers. He ordered his group to attack. 32 Thunderbolts dove into the German formation, throttles pushed to maximum, manifold pressures climbing past 75 inches of mercury. What happened next was unlike any air battle the Luftwaffe had experienced. The Thunderbolts didn't dogfight or try to outmaneuver the German fighters. They attacked at speeds exceeding 500 miles per hour, making single passes with devastating effect, then using their momentum to climb back to altitude before German pilots could respond. The sheer violence of the attacks disrupted German formation cohesion. Fighters scattered, trying to track targets moving faster than anything they'd encountered. The carefully planned mass attack dissolved into chaos. Lieutenant Francis Gabreski, flying as element leader in Zemke's formation, destroyed 3 Bf-109 fighters in a single diving pass. His combat report noted that the German pilots seemed confused by the Thunderbolt's speed, attempting deflection shots that missed by wide margins because they couldn't anticipate the American fighters' velocity. Gabreski's gun camera footage showed German fighters appearing to hang motionless as his Thunderbolt screamed past at closing speeds exceeding 700 miles per hour. The engagement lasted 43 minutes. The 56th Fighter Group destroyed 12 German fighters confirmed, with 8 more probable. More importantly, they had broken up the massed attack before it could reach the bombers. Of the 183 B-17 bombers that reached Leipzig, only 4 were lost to fighter attack. The mission was a stunning success, and it established a pattern that would repeat throughout Big Week. Thunderbolts, using maximum power from high-octane fuel, would shatter German formations before they could engage the bombers. But the missions took their toll on aircraft and engines. Maintenance crews reported unprecedented wear on engine components. Cylinders showed heat stress. Spark plugs fouled rapidly. Pistons developed microfractures from sustained high-pressure operation. The R-2800 engines were being pushed beyond their designed limits, and despite Pratt and Whitney's robust engineering, failures began occurring. On February 22nd, Lieutenant James Howard's engine seized during combat over Oschersleben. He managed to glide to friendly territory, but the incident highlighted the risks of sustained maximum power operations. Pratt and Whitney engineers rushed to Wright Field to investigate the failures. They discovered that the improved fuel's higher octane rating allowed such high cylinder pressures that mechanical components were failing from stress rather than thermal damage. The solution wasn't to reduce power, combat necessity made that impossible, but to strengthen critical components. Pratt and Whitney began producing reinforced pistons with thicker crowns and rings made from new alloys that could withstand higher temperatures. The modifications were retrofitted to operational engines within weeks, a testament to American industrial capacity. Meanwhile, Shell Oil's research team was working on another fuel improvement. Geoffrey Russell had recognized that the limiting factor wasn't just octane rating, but also fuel cooling properties. When compressed in the cylinder, fuel absorbed heat from the combustion chamber walls. Fuels with better cooling properties could prevent hot spots that led to pre-ignition. Russell experimented with fuel additives that enhanced heat absorption, effectively providing thermal management through chemistry rather than mechanical cooling. The new fuel formulation, designated ANF-32, reached operational testing in April 1944. It had the same octane ratings as ANF-28A, but included compounds that improved thermal management. The result was dramatic. Engines running on ANF-32 could sustain 78 inches of mercury manifold pressure for nearly twice as long before cylinder head temperatures reached critical levels. Pilots gained additional seconds of maximum power, seconds that could mean the difference between successful attack and getting shot down. The fuel's impact extended beyond just fighter operations. The bomber formations themselves benefited from improved escort effectiveness. With Thunderbolts able to maintain combat power longer, they could stay with bomber formations throughout the most dangerous portions of missions. German fighters, facing escorts that wouldn't disengage or run out of combat power, became increasingly cautious. By May 1944, Luftwaffe fighter pilots were showing reluctance to press attacks against well-escorted bomber formations. Major Heinz Baer, the Luftwaffe ace, noted in May 1944 that American escort fighters had become nearly impossible to evade. Their speed advantage was so pronounced that any German fighter that committed to attacking bombers would be caught by escorts during its attack run. The tactical situation had fundamentally reversed. Instead of American bombers being helpless targets, German fighters had become vulnerable. The psychological impact was devastating to Luftwaffe morale. But the Americans weren't content with tactical air superiority. They wanted total air dominance. In June 1944, as Allied forces prepared for the Normandy invasion, the 8th Air Force launched Operation Chattanooga, a campaign to destroy the Luftwaffe as an effective fighting force. Thunderbolt groups were authorized to pursue German fighters to their airfields, shooting them down during takeoff and landing when they were most vulnerable. The tactics were aggressive, dangerous, and only possible because American fighters had the power to outrun and outfight anything the Germans could field. June 6, 1944. D-Day. Allied forces landed on the beaches of Normandy while overhead, P-47 Thunderbolts flew continuous patrols. The Luftwaffe's response was feeble, fewer than 100 sorties against thousands of Allied aircraft. The contrast with previous years was stark. In 1940, the Luftwaffe had dominated European skies. 4 years later, it could barely contest Allied air superiority over its own territory. The transformation had many causes, but Geoffrey Russell's fuel formula had played a crucial role. The success of high-octane fuel in Europe prompted the Army Air Forces to accelerate its deployment in other theaters. In the Pacific, P-47 Thunderbolts began arriving in larger numbers, replacing earlier fighters. The Pacific presented different challenges than Europe. Longer distances between bases required better fuel economy. Higher temperatures stressed engines differently. Japanese fighters, particularly the Kawasaki Ki-61 and Nakajima Ki-84, had good high-altitude performance and couldn't be dismissed as easily as earlier Japanese designs. But the Thunderbolt's power advantage proved just as decisive in the Pacific as in Europe. Japanese pilots, trained in traditional dogfighting tactics, couldn't cope with American fighters that refused to engage on Japanese terms. The boom and zoom tactics perfected over Germany worked equally well over the Philippines, Formosa, and eventually Japan itself. By late 1944, American fighters dominated Pacific skies with the same authority they had established over Europe. The fuel's success created an unexpected problem. Demand exceeded production capacity. By summer 1944, the Army Air Forces was consuming over 50 million gallons of high-octane aviation fuel monthly. Shell, Standard Oil, Texaco, and other petroleum companies were operating refineries around the clock, but they struggled to meet demand. The exotic additives required for 115-octane fuel were themselves in short supply. Some relied on rare earth elements with limited availability. Others required complex synthesis processes that couldn't easily scale. Geoffrey Russell found himself coordinating a massive industrial effort. What had begun as a laboratory experiment had become a critical military supply chain involving dozens of refineries, hundreds of chemical plants, and thousands of workers. Russell worked with petroleum companies to optimize production processes, substitute more readily available compounds where possible, and develop new synthesis routes for critical additives. The effort was less glamorous than combat operations, but equally vital. Without steady fuel supplies, the entire Allied air campaign would grind to halt. By autumn 1944, production had stabilized at levels sufficient to support operations. The petroleum industry had proven once again that American industrial capacity could scale to meet any demand. But Russell was already thinking ahead to future requirements. Jet engines were on the horizon, requiring entirely different fuels. The Germans were already flying operational jet fighters, and though they appeared too late and in too few numbers to affect the war's outcome, they represented the future. Russell began studying jet fuel chemistry, preparing for the next revolution in aviation. December 1944 brought the Battle of the Bulge, Germany's last major offensive in the West. The Luftwaffe committed its remaining reserves, including some of its first operational jet fighters. American P-47 groups found themselves facing Messerschmitt Me 262 jets that could exceed 550 miles per hour, faster than any piston-engine fighter could achieve. For the first time since adopting high-octane fuel tactics, American pilots faced an enemy with superior speed. But the Me-262s had critical weaknesses. Their jet engines were unreliable, requiring complete overhauls after roughly 25 hours of operation. They consumed fuel at prodigious rates, limiting their combat endurance to less than an hour. Most critically, they were vulnerable during takeoff and landing when their speed advantage disappeared. American fighter pilots learned to position themselves near known jet bases, attacking the German jets when they were most vulnerable. Captain Robert Johnson encountered an Me-262 on December 23, 1944. The German jet made a high-speed pass at a bomber formation, then turned for home. Johnson, flying at 30,000 feet, spotted the jet as it descended toward its base. He pushed his throttle to maximum, dove, and intercepted the German fighter at 5,000 feet as it slowed to land. The engagement lasted seconds. Johnson's .650 caliber machine guns shredded the jet's tail section, and it crashed short of the runway. It was an inglorious end for an aircraft that represented the future of aviation, brought down by tactics enabled by the chemistry of the past. The Battle of the Bulge ended in January 1945 with German forces in retreat. The Luftwaffe had expended its remaining strength and would never recover. Allied air superiority was absolute. American fighters roamed German skies at will, destroying aircraft on the ground, attacking transportation networks, and supporting advancing ground forces. The P-47 Thunderbolt, powered by fuel that shouldn't have been possible, had achieved what many thought impossible 4 years earlier. It had transformed air warfare and helped secure Allied victory. February 1945 brought the strategic bombing campaign to its crescendo. With minimal fighter opposition, American bombers targeted oil refineries, transportation hubs, and industrial facilities. The Germans couldn't produce enough fuel to fly training missions, much less combat operations. Their synthetic fuel plants, critical to maintaining military operations, were systematically destroyed. The irony was profound. Germany had pioneered synthetic fuel production in the 1930s, developing processes to create gasoline from coal, but they had never achieved the octane ratings necessary for high-performance combat operations. Their fuel chemistry had lagged behind their aircraft design, and they paid the price. Geoffrey Russell received the Presidential Medal for Freedom in March 1945, though the award remained classified because the full details of his fuel formula were still military secrets. The citation praised his contributions to the war effort, without specifying exactly what he had done. Russell accepted the award quietly, more concerned with the moral implications of his work than with recognition. He had created something that gave American pilots a decisive advantage, but he had also contributed to the deaths of thousands of German pilots. The complexity of that legacy would occupy his thoughts for years to come. The war in Europe ended in May 1945. The Luftwaffe ceased to exist. The last German fighters were captured on the ground, many without enough fuel to fly. American fighter groups began transitioning to occupation duties. Their combat operations concluded. The P-47 Thunderbolts had flown over 154,000 combat sorties, destroyed over 7,000 enemy aircraft, and established air superiority that made Allied victory possible. And none of it would have been possible without a chemist who believed that octane ratings could go higher than everyone thought. The war's end brought assessment and analysis. The United States Strategic Bombing Survey examined every aspect of the air campaign, trying to determine what had worked and what hadn't. One conclusion was unambiguous. High-octane aviation fuel had been critical to American air superiority. Without it, American fighters would have been outperformed by German aircraft. Without it, escort operations deep into Germany wouldn't have been feasible. Without it, the strategic bombing campaign would have failed with catastrophic Allied losses. The fuel had been as important as radar, as important as proximity fuses, as important as any technological advantage the Allies possessed. Geoffrey Russell returned to civilian life and academic research. He continued working on fuel chemistry but shifted focus to commercial applications. The additives he had developed for military use found applications in automotive fuels, industrial processes, and synthetic materials. The knowledge gained from pushing octane ratings to unprecedented levels informed decades of subsequent petroleum chemistry research. Russell published papers on combustion chemistry, taught graduate students, and quietly influenced a generation of chemists. He rarely discussed his wartime work, preferring to let others tell the story. The P-47 Thunderbolt remained in service through the late 1940s, gradually replaced by jet fighters. Many were sold to Allied nations, where they served into the 1950s. Some remain flying today, maintained by warbird enthusiasts who preserve the aircraft as flying monuments. When these restored Thunderbolts fly at air shows, they still use high-octane fuel, still demonstrate the power that made them formidable. The sound of an R-2800 engine at full power remains unmistakable, a reminder of what American ingenuity achieved when chemistry met necessity. The legacy of Russell's work extends beyond aviation history. It demonstrated that scientific innovation could be as decisive as military strategy. It showed that breakthroughs could come from unexpected places, from researchers willing to challenge conventional wisdom. It proved that the rules could be broken when circumstances demanded it. And it reminded everyone that war is won not just on battlefields but in laboratories, factories, and refineries, where dedicated people work to give their side every possible advantage. The chemist who broke the rules gave American pilots the power to dominate the skies, and in doing so, changed the course of history. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.